All right. Going live, and we're live. All right, good evening. So this is the last minute live stream I was able to pull together for Unit 8. We have our test tomorrow, and I hope you guys are doing good, by the way. We had a good weekend. So we have our test tomorrow, and I know many of you were absent the last couple of days, Friday, maybe Thursday, maybe both. Hopefully this helps you because honestly, Friday we reviewed in class. There's gonna be a lot of overlap. There's gonna be some new things too, actually. So even if you even if you were in school on Friday and you saw the review we did in class, there's gonna be maybe another take on something. You'll notice some similarities. But anyway, this should help prepare you. And of course, doing the review guide should help as well. So I am here. I will answer any questions you have. You can either put them in the chat or put them on Remind, and I will get them there and answer the questions. So let me know if you see any technical difficulties. Like I said, I kind of threw this together at the last minute, and yeah, seems to be working good though. So I'm going to continue here, trying some new things as well. So that'd be another thing that might go wrong, but hopefully you won't even notice anything. So let's get right into this. This should kind of, hopefully this is gonna be a shorter one. This is the first time I've ever done a live stream review for Unit 8. I don't know in the past, it's just never been a big deal. Maybe I just thought that the thing we did in class was enough, but here we go. I don't know how long this is gonna last, but clock's ticking, so let's do this. All right, so first of all, what happens when you break a bar magnet in half? Okay, little things like this, just be aware of. All right, great. It's actually not B. So I'm glad I asked this. So when you break a magnet in half, first of all, it has nothing to do with charge. I mean, charge is related to magnets, but like questions or choices like D are just like so wrong. Like it has nothing to do with like a positive and negative. Like plus and minus have nothing to do with north and south. Nothing. Okay, so just kind of get that separated in your skull. All right, yeah. And so like this letter C has like the keyword in there, but again, kind of look out for that. That's not what happens when you break it, even though it kind of seems maybe logical. But the answer is going to be A. Yeah. So you're going to each become magnets. You get two baby magnets, and they're both going to have a north pole and a south pole. In fact, you can keep breaking those magnets in pieces, and every single little piece is going to be a magnet. That's like the whole point, right? Like even if you go down to the atom of an iron magnet, the iron atom itself is going to be a magnet, right? So that's the whole idea. So the answer is definitely A. All right, you cannot separate north pole and a south pole. So north pole and a south pole, not separatable. That's not even like a thing. It's not even a choice. Okay. All right. Let me know you got questions. I will always go back. Like I said, there's usually like a 10 to 15 second delay. So I might not see your question until I'm already talking about something else, but I can always go back. You know, it's kind of like that's the nice thing about being live. All right, the source of all magnetic fields. Now this was a question on the quiz as well. And by the way, this is, well, if you pay attention to this, and I'm gonna go back 2 slides because just watching this is better than nothing, maybe having it on the background, okay, better than nothing. But the more you are engaged with this, the more you are paying attention, the more you are making this your primary focus, the better off you're going to be. We've got 2 more tests in this class. Tomorrow's test is one of them, and then we'll have 1 more. So if you really want to finish this semester off strong, then you want to pay attention, all right? So, okay, focus for like this. Hopefully it's like 20 minutes, maybe 45 minutes, I don't know. I keep going back and it's gonna be a lot longer, but all right, so the source of all magnetic fields. Again, this was a quiz question. It's always a good idea to go back and check that quiz to see what things you might have gotten wrong there, or maybe you guessed at and got right, just to go back and check all the questions. So the source of all magnets is, and I will say this one more time, this is absolutely so wrong, all right? It has nothing to do with negative charges lining up, has nothing to do with gaining electrons, none of that, all right? It's just when you get charged particles that are moving, you get a magnetic field, all right? That is it. Charged particles are moving. That is the only relationship to charges when it comes to a magnetic field, all right? Charged particles move and they create a magnetic field perpendicular to its motion. That's it. So none of this like positives over here, negatives over there. That's like totally a separate thing. Okay, it's just out of your mind, out of your mind. Get it out of your brain. Okay, what makes a piece of iron magnetic? Look at this, me sneaking more of these in there. Because guess what? Every year people put like choose choices that involve those, and it's like I just want to make sure no. Okay. So the makes a piece of iron magnetic is that all the domains are mostly lined up in the same direction. All right. So that's what makes iron magnetic. So the domains are lined up in the same or mostly the same direction. So speaking of domains, what is a domain? A domain, yeah, this is one of those things you just gotta memorize, right? This is like the one vocab word, one vocab term. And letter C is kind of a charged particles again, right? No, I made this up today, so like I'm not like surprised by it, or this disgust is like just I did this myself, but yeah. A magnet. So the question on the quiz was a lot of you guys picked this one. The domain is not the source of all magnetism. It's just when you've got like this is a this is a I like chocolate. So a domain is magnetically aligned atoms. This diagram here that I just Googled today, it's not showing atoms, it's showing like clusters of atoms. And so that's what it is. It's a group or a cluster, a group of atoms that are all aligned. So you got these little mini magnets inside of a piece of metal, piece of iron. And they can, when they line up, they do this kind of thing and it becomes a magnet. The whole thing does. All right. So again, this is all also on the notes. So if you want a like document, it's like I think 2 pages long. If you were to print it out, Word document, that is there's other diagrams out there. Okay. All right. By the way, like my new little glowy thing I made since last stream. I think I was printing that out last time we did a stream 2 weeks ago. So it's a 3D print back there. Yeah. So Zelda is one of the best games ever. I mean, all the Zelda games. Anyway, I like Zelda. I like games. But balance in life. Why does heating a magnet or banging it on something hard weaken it? So like when we did our little labs, I was like, try not to drop the magnets, and then we can remagnetize them, like a long time ago, a couple weeks ago. Why does heating a magnet or banging it on something hard weaken it? Okay. Now there's and I said this on Friday too, there is a built-in assumption here is how do you weaken a magnet? And heating a magnet or banging it on something hard will weaken it. So it's not A, okay? You can't freeze. I mean, you could freeze a magnet, but it's probably not gonna do anything to it except make it cold. Yeah, so basically, yeah, D is not it. The answer is B. The domains get knocked out of alignment. So it's sort of like the reverse of the picture I showed you last slide. It's like, so this is the same picture. It's basically if you bang it into something or you heat it, the heat adds energy to all those little domains and they just basically get jostled out of alignment is the word I used on Friday. They get jostled out of alignment. So it goes from a nice organized magnet to basically that. It just knocks it out. Or if you add heat to it, it just like adds energy and all the molecules start to unalign. So that's what happens. So again, heating it or banging it on something hard, hitting it will weaken the magnet. Okay. All right. And this one I said on Friday, it's like sort of just out there. It's like all of a sudden we're talking about the Earth's magnetic field. And that's because, well, the Earth is a giant magnet. And so it's a reasonable question to ask. Why does the Earth behave like a giant magnet? What's the deal with that? And as far as they could tell from all the evidence that they have, it is not magnets in the ground. It doesn't make sense because they would be like random in the ground. The core of the Earth is not a giant magnet. It's because it's liquid. It's like, melty and hot and gooey in there. It's not the Earth's rotation. There's Mars and the Moon and a bunch of other planets will rotate, and they don't have a magnetic field. It seems to be the flowing magma under the Earth. So if you like Google the Earth's magnetic field, it's kind of weird. Like it's not a perfect thing. And I mean that kind of makes sense. If you have like this flowing magma under the Earth, that's not going to be like a perfect bar magnet. All right, that's probably, again, even if you don't understand it, just memorize it. Okay, some things you just have to memorize. What 3 materials can become magnetized? You know this. Okay, not copper. Okay, copper seems like it could become magnetized because we keep making our coils out of it, but it's only because we run a current through the copper that it becomes a magnet. Okay, as soon as the current is off, the magnet is off. It's no longer a magnet. So copper in and of itself cannot be magnetized, but it is a conductor, electrical conductor. And so if you run current through it, it will become like you have moving charges now, and those moving charges create a magnetic field, but the copper itself does not become magnetic. So hopefully you know it is iron. I always say iron, nickel, and cobalt is the typical order that I say it in. I think I have it in all the notes. Okay. So iron, nickel, and cobalt. I put them slightly out of order here, because it's tricky. But iron, cobalt, and nickel. Again, just memorize and you're good. Okay, so rank the marked positions in order of magnetic field strength. Where is the magnet the strongest? I will write this down, and while you're ranking them in your head, it's strongest at the poles. Okay, so what you gotta do is look like, how far are they from the pole? Okay, so if you look at these distances from the pole, then it goes A, B, C, and then D. Okay, I don't know if you were putting it in the chat or not, but there it is. So strongest at the pole. So you have to look at the distance from the pole. B is like really close to the magnet, but it's really kind of far from the pole compared to A. All right, A is the closer one. B is closer to the magnet, but that's there, I put that there to be tricky. Not tricky, but just to make sure you get it. Like I say tricky, but I'm kind of like half joking. I put it there just to make sure that you got it. All right. Boink. Which one most correctly shows the shape of a magnetic field around a magnet? I did not make this one. This one's just from Google. Well, it's not going to be A. If you see straight lines, I mean, that's not it. C is sort of tempting, I guess, but they don't go back to themselves. Like it's like, what is going on there? That's not right. Same over here. What? So C is not it. So we're between B and D. I'll just say that magnetic field lines always go from north to south. So it's going to be B. Because it goes from north to south. But honestly, if you just remember, hey, wait a minute. Yeah, we're good. Okay, it doesn't even matter. See, look at this one's like whoop this way, and all of a sudden it's like whoop returning trip that way. That's not how it goes. It's always from north to south. So it's a one-way trip from north to south, whatever side of the magnet you're on. Even if you're coming up out of the screen, all right, it's still from north to south. So B is the correct answer. All right, weird question, but which magnet pulls with more force? We got this giant magnet on the right. Oh, look at this. I don't know why I got that. Okay. Like I said, I just made this today, so I'm going to have some typos. There's one. Which magnet pulls with more force? Small magnet A, giant magnet B, or are they going to pull the same amount of force? It's a weird question. But the answer, I mean, it's not weird. It just seems a little out of place here. But it's always good to remember like Newton's third law. For every action force, there's an equal and opposite reaction. So an opposite. Okay. Focusing on the equal here. Why am I bringing this up now? Trust me, all right? This is going to involve one of the questions on the test. Like, you know that, like, okay, by itself, B is a strong magnet compared to, I mean, just based on the size. B seems like it's going to be a stronger magnet, but it doesn't matter how strong you are. It's always going to be equal and opposite, okay? So remember this one. Like, although I'm making like a thing here so that you like can remember this part right here, all right? Or I guess this thing. Remember this. Let's try this. There we go. All right, remember this. It's equal and opposite. So it doesn't matter the size or anything like that. Force is always, here, I'll even put the word force. The force is always equal and opposite. Yep. All right, these might look familiar. Which shows two magnets with opposite poles together? Opposite poles. A or B. A or B. Opposite, opposite, opposite. Okay. Hopefully you know the answer is A. Okay. Why? Look at B is showing you going from north to south. So like these are literally going from north to south, these lines. So one of these is going to be north. I don't know which one is which. I'm just picking one. And that would mean like this one would be like two norths or maybe two souths. Like it's like, no, I don't want to go toward a north. I want to go toward my south buddy over there. Wouldn't quite look like that. It would probably look more like a back and around. But you got here too. So in fact, I don't like this one drawing there. That's going to go like up and over. All right, it's going to go around. So same thing over here. Like it's going from north to another north. Or rather, it's not going to go from a north to another north, unlike letter B. Okay, so opposites. So these are. Oh, hey! I just got done explaining all that, and then I like realized that I answered the wrong question here. So the actual answer is B. So if you stopped watching the video like 10 seconds ago, you're gonna get this one wrong. So this is opposite poles. All right, literally I wrote that here. North and south are opposites of each other. So these are like poles, and these are opposite poles. So I'm gonna be very clear here. Okay, like poles and opposite poles, as it's written there. Good. All right. Weird error for me to make, but it kind of goes to show that you have to kind of like focus on stuff. Because if you focus on stuff, if you don't focus on stuff, like for example, you're focused half on trying to produce a live stream and there's like little things going on in the background you got to keep, or if you're, I don't know, whatever you're focusing on when you're trying to study or even take the test, try to focus and stay focused on one thing at a time. All right, what happens to a compass when it's placed in a magnetic field? So a compass is a little magnet. Okay, I have one hanging from the ceiling in the classroom. Not a compass. I have a magnet hanging from the ceiling in the classroom from a string. And whenever you do that, it becomes a compass. And so what does it do? No positive or negative charges. All right, what does it do? It aligns itself parallel to the magnetic field lines. All right, magnetic field lines love to line up parallel to each other. You see the word perpendicular. Perpendicular is associated with, what do you call those? Electric field lines. So we're going to talk about that momentarily. I could talk and write at the same time. Apparently not. Lines. Field lines. So when we talk about the word perpendicular, that applies to magnetic and electric lines. But when you're talking about magnetic and magnetic will line up with each other, parallel. All right, just like we saw right here. All these little lines are parallel to each other. Okay. All right. So next question. What direction is the current in the wire here? All right, if you were here Friday, this looks familiar, but I kind of did like a little flippity floppity on this one, so it's kind of new. To help with this, I have another camera. This one is pointing at my screen, so hello, everybody. So, because I want to show you, okay, first of all, and I apologize, yeah, part of my like boom is in the way here because of my microphone. But it's okay. So I'm going to help you with this. First of all, do you use the right hand or do you use the left hand? Okay, I don't know. Well, actually I do, but let's see. it's asking what is the direction of the current, and it shows you a magnetic field. Okay, so there's only two things mentioned. There's no mention of force, so I'm going to use the right-hand rule. Okay, now the way this is going is it's going like sort of behind, like I'm going to wrap my fingers in a way that shows the direction of the magnetic field. So I'm going to take my right hand and I'm going to use my fingers to point in the direction of the wire. I'm sure I have a wire somewhere here. I do. It's in a knot, of course, but I'm going to hold a wire here. This is unplanned, you could tell. But I'm going to grab this wire just like it's the wire in there, and I'm going to wrap my fingers around in the direction like it seems to, it disappears behind, like the magnetic field disappears behind the wire, and then it comes out in front of the wire. So disappearing, going right, coming in front of the wire to the left. And so I'm going to do that, going in front of it to the left, going behind it to the right, and my current is going downward. It's going in the direction of my thumb. All right, so using the right hand, it is going downward. So I didn't write that on there, but I guess I could. Let's get rid of that camera. And then, all right, so the current is going down. Okay, so what direction is the current? Downward. All right. How about this one? Okay, once again, this might look familiar-ish if you were here Friday. Again, I'm going to use the right-hand rule or the left-hand rule, and the answer is, since there's only mention of, well, there's not even a mention of it. It's just like, it asks about the current, so that's one thing. It shows you the magnetic field lines, that's two things. And there's no mention of the third thing, there's no mention of force. So it means I'm going to use my right hand, okay? Whoop, hello again. So my right hand coming in at you from the right, at least that's what it looks like for me. I'm going to curl my fingers to match the arrows. Okay, the arrows are pointing like this, not like this. See, that's the opposite. They're going like down, and I'm going to complete the thing. And my thumb is facing out of the screen. So the answer is out of the screen, right at you, thumb in the face, okay? That's the direction of, I just did something. That's the direction of the current. So out of the screen. Hey, wait a minute, I meant to get rid of that screen. Oh, I locked it in place, even worse. Okay. So, where'd my thingy go? Pen, there it is. All right, let's write. Oh, hang on. What is going on? All right, there we go. All right, so it is coming out of the screen. So if I wanted to make the little like symbol for that, it would be a dot with a circle around it, coming out of the screen. Okay, that's the direction of the thingy. Right, what's the direction of the magnetic field at X? So this one has a current. Current going to the right, going to the left. There's no mention of force. So once again, I'm going to use my right hand to do this. And what I'm going to do in this case, it wants to know the direction of the magnetic field, and it gives me the direction of the current. So I'm going to take my right hand, I'm going to point my thumb in the direction of the current, which is to the left here. And this one's a little bit tricky, kind of, sort of, maybe, but it's like the wire's going this way. And then at the X, look what's happening. So I'm going to curl my finger. It's going to go around the back of the wire and come out at the X, right? Like at where the screen is at. That's where the current, that's where the X is at. So what's happening right at the screen, at the X, if I point my thumb to the left and I curl my finger around the back of the wire, because that's what happens right at the X. I'm not gonna go like this because that's like weirdly, that's not, I'm like right at the X, right where it like crosses the horizontal plane. The magnetic field is coming out of the screen at me, okay? It's coming out of the screen. So I'm going to write that here, out of the screen. And if I attempt to draw that, basically what happens is it goes in front, and it goes behind the wire. I'm really bad at drawing this. And then as it comes out, if I would, like, this is like coming out of the screen right here. Okay, it's really hard to draw. I know. I saw. I don't understand it. I know. It's hard to, you got to envision this three-dimensionally, okay? I'm not going to be able to hold a wire, but I'm going to try. No, it's not going to work. You know what? I'm going to just hold up my pen. My pen is facing, what if I turn this camera back on? Okay, so my pen is facing in the same direction as the wire right now. So my pen is showing the direction of the current. Okay, and the magnetic field is going to go around the back, up the front, back, down, up, back, down, forward, up. It's kind of hard to tell. I mean, this is like a video, and like so it's two-dimensional, but I'm telling you what's happening. So it goes down, out, up, and then back over, back, down, toward the screen, up. Okay, so where the X is right here at the bottom, that's where it's coming out of the screen. All right, so if I were to hold, so do this, like try this, hold it so that your fingers are kind of hovering with the pen right in the middle of it, and you're going to see like right, even with the line of your pen, even with the line of the wire, that's where that's where the magnetic field is coming out of the screen. And then it's going to continue to curl up and back around over the top. But I'm not asking about that part. I'm asking about the part where the X is, which is underneath the wire. So under the wire, what is happening? And what's happening is that the electricity is, since the electricity is going to the left, the magnetic field is coming out at that point. Okay. I'll do one more. See what happens. Okay. So I got another one. What's the magnetic field? What direction is the magnetic field at the X? Okay. It's like literally the same exact wire as before. I just flipped it upside down. So what's happening here? Same thing as before. The wire, let me put that window back up. So the magnetic field is going to the left. So I'm going to point my thumb to the left, and I'm going to kind of like pretend to grab it. And like, so what's happening? The X is right above the wire, right? So directly above the wire, go straight up from it. What is the direction of the magnetic field? And the direction of the magnetic field is going into the screen, because that's what my fingers are doing. Right, everything's getting in the way, but that's the problem with three-dimensional stuff. So at above the wire, above the pencil, my fingers are going into the screen before they start to come back around. Okay, so at the X, it's going into the screen. I need that pen. So my answer is into the screen. Now I'll try to draw it again, but basically what's happening, it's going into the screen here, and then it starts to come down, 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 and then it's going to go behind the wire, and then it's going to come forward. Okay, it's curling back forward toward the front. This is where the previous question was coming out of the screen, and now it's coming out of the screen right here. And what's going to happen is, while it's out of the screen, it's going to go in front of the wire, upward. It's going to go up, 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 and then it's going to curl back into the screen right there before it continues its loop. Okay. It's three-dimensional. Yeah. All right. Try it with your hands. Try it. If you're still having trouble with that, just try it out. All right. This one is, it says a current carrying wire runs through an area with a magnetic field going into the screen. Okay, which you can kind of tell by these little circles with X's in it, meaning that's like the arrow going away from you. So the magnetic field B is going into the screen. It tells you that the current is going to the right. There's my I going to the right. What direction is the force on the wire? All right, now it uses the word force, and it talks about current, and it talks about magnetic field. So that's three things. So we're gonna have to use our left-hand rule here. And so Let me turn on my little screen again, see how this goes. Can I lock that without? Good. So I use my left hand. And this is gonna be a little tricky because this is my left hand. I gotta reach around a bunch of stuff. All right. So left hand rule. First you make the L. And then with the L, I'm gonna try to do this. You gotta stick out your middle finger about halfway to make it perpendicular to your other two fingers, okay? Let me see if I could do it this way. No, it's not gonna work, but okay. So from this angle, I can make like the gun, which is unfortunate, but I can't make the L without like breaking something. And then, oh, I could go this way. And then I turn it this way, let's say. I'll do it. And then I just basically stick my middle finger up again and see how it's like perpendicular to the other two things. So my middle finger is perpendicular to my pointy finger, and my middle finger is perpendicular to my thumb, which is right there. Okay, so they're all perpendicular to each other. And so what I do here is I'm going to attempt to write on this while it's there, right? So I don't have the picture here, but I'm going to do this. It's F, B, I. The force is your thumb or thumb, you know, however you say it. B is your pointy finger. And I is your middle finger. Okay. So there's diagrams there's diagrams out there. So I'm going to take and I don't know how this is going to work, but we'll try it. All right. So I is my middle finger. I'm going to point it to the right, just like it is. Okay. See, if I tried to do it up here, everything would be backwards. That's why I got this extra camera set up here. So, all right. And now I'm going to keep my middle finger pointing to the right. And I'm going to, so B is going into the screen. So B is my pointer finger. So it's already doing that. So that's kind of nice. And so with my middle finger, which is current, pointing to the right, and my pointer finger, which is my current magnetic field, is pointing into the screen. My thumb here, which is the force, is pointing up. So one more time, current, which is I, which is my middle finger, is pointing to the right. B is pointing into the screen, my pointer finger, and that leaves my thumb pointing upward. So that means that the answer is upward. Okay, so I'm going to write that. The direction of the force is upward. Okay, or I guess I could just go like that, because if you're looking at this like with the screen down flat, it's toward the top of the screen is really how it would be. Toward, what is that letter? Toward top of screen. Okay, because if I say up, I mean, like I said, depending on the angle of your computer screen right now. Okay, so here's another one. This is a question, we haven't really seen it in this way before, but it's still the same idea. A charge is moving through a rightward magnetic field such that it experiences a downward force. What direction is the charge moving? Okay, so we've got force mentioned right away. That tells us it's going to be our left-hand rule. The magnetic field is moving to the right as indicated in this diagram. So B is to the right. And it wants to know what direction the charge is moving. It's a little confusing because it looks like this arrow is showing the direction of the movement, but that is the direction of the force. So I'll just be clear here. Force vector. That's the force arrow, not current. Okay. So how do we do this one? All right, let me turn on my other screen here and let's line this up. So I think I got to come in from this direction. So B, all right, so again, I'll write this up on the screen. F is thumb. B is pointy. And I is middle finger. So, excuse me. Alrighty, so right away, let's see. Okay, so thumb is pointing, okay. So thumb is pointing downward. This is not going to work very well, is it? I'm blocking the whole thing. Okay, Well, no, I'm not, because it's also it's right there, so I don't have to block anything. All right, so thumb is pointing downward because that's the force, that arrow pointing down. B is my pointer, so I got to come at it from, how am I going to do this? So on the test tomorrow, feel free to, like, you know, do weird things with your arm to make this work. All right, so thumb is pointing down. I got that right. That's the force. B is my middle finger. Oh boy, that's got to point to the, what was I thinking when I made this question? Apparently I wasn't. All right, does this work? Thumb is pointing down. B is my pointer finger. That's got to point that way. Okay. Oh, that hurts. But you know what? If you get a good grade because of this, then that works. So B is pointing down. B is pointing down. My, let's start that over. F is pointing down. B, so F is my thumb pointing down. B is my pointer finger pointing to the left. And that leaves my middle finger, which is the current, pointing directly at you. That means that the direction of the current is coming out of the screen, okay? Try that yourself. I'm gonna try that over here. I got, like, I can't move. You're able to move a little bit more than I do. So like, it's just kind of like extra difficult for me. So it's not supposed to be this hard. So force is down. Oh, this might work. Force is down. No, it doesn't. Org. I got twisted. All right, let's do it this way. All right, I'm a little farther from the, all right. Bottom line is it's coming out at you. It's coming out of the screen. So you saw my attempt. So out of the screen. Okay. Now, really quick hint. Everything should be perpendicular to everything else. So if the magnetic field is moving left to right, and the force is moving left and right, and the force is moving down or up, that means that the magnetic field either has to be coming out of the screen or into the screen. All right. So that's the trick. It's got to be, like, remember, 3 axes and 3 axes, and that's the. If you do the hand thing right, you won't need to remember that. All right. Any last questions on that kind of stuff? Just take practice, right? Try the review. Try doing the things I just showed you on your own. All right. My phone went dark, so I'm going to open up. Okay. So I want to make sure I didn't get any reminds in the meantime. All right. Which would cause a current in a circuit? A closed circuit moving perpendicular to magnetic field lines, an open circuit moving perpendicular to magnetic field lines, a closed circuit stationary in a strong magnetic field, or an open circuit stationary in a strong magnetic field. 2 things here. First of all, the word stationary, things have to be moving. So that's like a big clue that that's not going to be the right answer. Okay, something has to move in order for this to work. The other clue is perpendicular is right. Okay, everything's got to be perpendicular. And the other thing is you're not going to get a current if you have an open circuit. All right, open circuit is like the switch is open. Okay, remember this thing? It's like boom, that's an open circuit. Okay, no current. No current. So the answer is going to be A. It has to be a closed circuit, so that a closed circuit means there's a complete path. The circuit has to move perpendicular to magnetic field lines, and I should underline moving. Okay, there you go. We're almost done. Motors, generators, and electromagnets have a lot in common, so that's something to keep in mind. I did one thing that's not going to be on this review that was on Friday's review is just a little summary of those 3 things. So when you're done with this, maybe go back and open up that PowerPoint and just go to the very last slide of that PowerPoint. Last slide in the review PowerPoint. Review, same thing. review PowerPoint. Okay, and you'll see what I mean. Okay, so check that out. That'll help summarize everything you need to know about that. I'm going to pretty much summarize the summary. So everything you need to know, I'm going to summarize right here. But if you want to see everything in a bigger context, that would be a better thing to check out. So how can a motor be made stronger? So as you answer this question, think about the other, like kind of keep this in mind for the other ones as well. We could choose more than one. So can you increase the number of loops in a coil? That would mean going from like, just a couple loops to like a lot more loops. So if you remember with your electromagnet, if you had all the coils all like on one end, that made it a lot stronger. And if you made your coils tighter, it made it a lot stronger. So A is a good answer. What about increasing the strength of the permanent magnet? Well, yes. If you used a weak magnet, it's not going to spin very well. If you, like some of you guys when we did the motor, when you did this thing, some of you actually doubled up on the magnet. Like you had a magnet and then you like put another magnet on top and it like spun faster. Okay. In fact, that's what the question's asking. That was like on top of the battery. So there's my battery. Okay. It's a weird battery, but you get the point. Increase the current running through the coil. Yes, that would do it too. So all these things. So increase the current running through the coil. Not only that, but these are all proportional, right? So if you were to, I don't know what that is. If you doubled the number of coils, number of loops, you're going to get double the strength of the motor. If you double the magnetic strength, you're going to get double the strength of the motor. If you double the current, you're going to get double the strength of the motor. So everything is proportional. It's all proportional. Proportional. I think I spell that right. Okay. So it's all proportional. More is better. More of everything means everything else is more. Okay. Now, one thing you needed to be able to do is explain how an electric motor works. Would be a very good idea to know how that works. And essentially, there's these three parts: a coil of wire, a battery or some other voltage source, and a permanent magnet. Okay, this picture is from the instructions that you have on your OneNote to make the motor. So even if you weren't here to make the motor, you could check this out and it'll explain it. Basically what happens is when it's touching, when you've got connection, you have a current in the coil, turns it into electromagnet. So this coil of wire becomes an electromagnet with a north pole and a south pole. Okay, here, north pole and a south pole. Then that gets repelled by the permanent magnet, or attracted if it's the other way around. Then the current has to either switch direction or alternate between off and on so that the permanent magnet will always repel the coil. So in other words, if we just left this connected, the south pole would swing around and it would basically just stay there because now it's attracted to the north pole. So what we did was we made it so the electricity turns off and then it just kept swinging until the north pole was back around here and it got pushed and then it just got pushed and then it got pushed. Okay. Real motors, like more advanced motors, will switch the direction of the current so that it's always being repelled every single time. Okay, so check that out. Make sure you got that. And again, like you don't have to get in like excruciating detail, but be able to explain the basics of how electromagnet and motor and a speaker works. You built one. You probably built one. If you didn't build one or the other, you'd still be fine on the test. It's okay, but everything I just kind of explained, the electromagnet is just a coil of wire wrapped around an iron core. And a speaker, again, if you weren't there the day I showed you the speaker, you're going to be okay. But in fact, if you weren't there, you're going to be fine. Okay, just make sure you know how to do the other things. So I should say or a speaker. All right. Any questions? That should say Unit 8. Now it does. not much to this test. It's going to be a shorter test. Okay. There's no math. So like, there's not a lot to this test. It just is what it is. I believe there's like 30-ish questions. There might be like 29 multiple choice questions and a couple FRQs. All right. So it's almost like a big quiz. So there's not a lot to really need to know. Just go through the review guide, check out the quiz that you did, look at the notes. And I mean, if you just got done watching this, that's great. All right. All right. Well, you have a fantastic evening, and I will see you tomorrow. Take care.